Over the past month, the internet buzzed with news about LK99, a material touted as a potential room temperature superconductor. Superconductivity allows electrons to flow through a material without losing energy to resistance, enabling lossless power transfer. While superconductors already exist, they require extremely low temperatures to function, limiting their practicality. For instance, MRI machines use superconductors to generate powerful magnetic fields to image the human body by manipulating hydrogen atoms. Similarly, maglev trains employ superconductors to levitate and propel trains at unprecedented speeds. However, the need to cool these materials to near absolute zero makes large-scale applications challenging. A room temperature superconductor could revolutionize technology, enabling a global energy grid that transports power without losses. Solar farms in Africa and Europe could supply electricity to the Americas during their night, and vice versa, balancing the intermittency of renewable energy across day, night, summer, and winter. This could provide cheap, clean energy worldwide, making room temperature superconductors a holy grail of technology. Over the past 2 decades, numerous claims of room temperature superconductors have surfaced, only to be debunked, often amid allegations of academic misconduct. The recent LK99 announcement sparked global excitement, with researchers racing to replicate the findings. However, skepticism persists, as early evidence suggests LK99 may not live up to the hype. To understand why this technology is so elusive, we need to explore how superconductors work, their current applications, and the challenges in achieving the next milestone in human technological progress. Superconductors are materials whose electrical resistance drops to zero below a critical temperature, typically near -273 degrees Celsius. In theory, an electric current in a superconducting loop could flow indefinitely without a power source. While indefinitely is hard to measure, practical examples demonstrate this durability. In Belgium, a superconducting sensor has measured gravitational forces for over 28 years without current loss, using a superconducting sphere levitated in a coil to track gravitational changes. Superconductivity is surprisingly common. Nearly half the elements in the periodic table exhibit it at low temperatures, and combining elements or applying pressure increases the number of superconducting materials. The mechanism behind superconductivity was initially mysterious. In 1957, 3 scientists published a groundbreaking paper explaining it. Above absolute zero, molecules in conductors vibrate, slowing electrons as they collide with these moving atoms, causing resistance. In superconductors, at very low temperatures, these vibrations diminish. Electrons, which typically repel each other, form pairs called Cooper pairs. These pairs act as a single particle governed by quantum mechanics, and can only absorb energy at specific intervals, creating an energy gap. At temperatures below 40 Kelvin, other particles lack the energy to disrupt these pairs, allowing electrons to flow without resistance. In 1986, this understanding was challenged when IBM researchers discovered ceramic materials exhibiting superconductivity at higher temperatures, around 93 Kelvin, just above liquid nitrogen's boiling point of 77 Kelvin. Liquid nitrogen is relatively inexpensive, costing as little as 15 cents per liter, making these high-temperature superconductors more practical. These materials, with complex crystal structures involving copper oxide layers, didn't fit the conventional Cooper pair model, leading to their classification as unconventional superconductors. While their exact mechanisms remain unclear, this hasn't stopped their use in innovative applications. One such application is a superconducting transmission cable in South Korea, connecting 2 substations in a growing residential area south of Seoul. The existing conventional high-voltage lines struggled to meet rising power demands, and adding another would have required costly new transformers, for which there was no space. Superconductors offered a solution. High-voltage lines reduce power losses over long distances, but homes require lower voltages, necessitating transformers. With superconductors, power can be transmitted at lower voltages without losses, eliminating the need for additional transformers. In 2019, This became the world's first commercial high-temperature superconducting cable, a 1-kilometer AC line carrying power in 3 phases. Liquid nitrogen, pumped at 66 Kelvin, cools the cables, which are encased in a stainless steel vacuum chamber to minimize heat leakage. Despite this, some heat raises the outlet temperature by 3 Kelvin, equivalent to the energy loss of 30 household refrigerators. However, high-temperature superconductors face challenges. The superconducting tape, wrapped around a copper core, is brittle with lower tensile strength than conventional conductors. The South Korean project benefited from straight conduits, avoiding bends that could break the tape. The high cost of superconducting cables, hundreds of dollars per kilometer, compared to $10 for traditional cables, limits their economic viability. The South Korean project was a unique case where the benefits justified the costs, but widespread adoption requires cheaper materials and cooling systems. The excitement around LK99 stemmed from its reported levitation, a hallmark of superconductors via the Meissner effect, where magnetic fields are expelled, causing the material to float above a magnet. However, levitation alone doesn't confirm superconductivity, as diamagnetic materials like water can also levitate in strong magnetic fields. Diamagnetism occurs when a material generates an opposing magnetic field, redirecting external field lines and creating a repulsive force. Measuring this involves suspending the material in a magnetic field and recording weight changes. For superconductors, diamagnetism data shows a sharp transition at the critical temperature, becoming perfectly diamagnetic as all magnetic fields are expelled. The LK99 announcement raised red flags. The South Korean team published 2 papers on a preprint server, one with 3 authors and another, 2 hours later, with 5, suggesting internal disputes over credit. One author later claimed the paper had errors and was published without consent. Despite clear replication instructions, results from 11 labs worldwide were inconsistent. Videos showed LK99 levitating, confirming some diamagnetic properties, but resistivity data was less convincing. The South Korean team reported a sharp resistance drop at 380 Kelvin, but replication samples showed drops at temperatures ranging from 100 to 400 Kelvin, and resistance never reached 0, indicating impurities. A German team created a pure LK99 sample using inert gases, resulting in a transparent insulator with some diamagnetic properties, not a superconductor. Despite this setback, the pursuit of room temperature superconductors continues. High-temperature superconductors, like those in South Korea, are already transforming urban power grids where space and demand constraints make them viable. As material and manufacturing costs decrease and efficiency improves, their applications could expand. The potential to transmit vast amounts of electricity without losses over long distances could reshape global energy systems, making clean energy more accessible and reliable. The enthusiasm for LK99 reflects the transformative potential of superconductivity. Researchers who believe they've made such a discovery are understandably eager to share it, as it could cement their legacy. The electrical grid, a complex and fascinating system, underscores the importance of these advancements. Spanning continents, power grids are among the largest machines ever built, driving economies and creating thousands of jobs annually. Fields like energy commodity trading, where algorithms account for renewable fluctuations, and global politics, highlight the grid's dynamic nature. For those intrigued by this field, learning opportunities abound. Courses in electricity and magnetism, programming, algorithms, and data analysis provide foundational knowledge for careers in energy and beyond. Platforms like Brilliant offer interactive lessons that make complex concepts engaging, with mobile apps for learning on the go. Their curated courses, including topics like AI, neural networks, and engineering, cater to diverse interests. By exploring these resources, anyone can start mastering the principles behind transformative technologies like superconductors and the global energy grid. In conclusion, while LK99 didn't deliver the promised breakthrough, the quest for room temperature superconductors persists. Current high-temperature superconductors demonstrate practical applications, but their limitations highlight the need for further innovation. As research continues, the dream of a lossless global energy network remains within reach, promising a future where clean, efficient energy powers the world. The journey to unlock this technology is as complex as the grids it could transform, but each step forward brings us closer to a revolutionary leap in human progress.